Hi, I'm Julia Winter, and today we're with Roberto Peverati from Florida Tech, and we're talking about density functional theory and introducing that in an upper level undergraduate class as a laboratory class. So, first of all, I just want you to tell me the name of your paper. I love it. It caught my eye on Chem Archive, and I want to hear about your density functional lab class.
Sure. Thank you, Julia. First of all, let me just say that I'm honored to speak with you. It's a pleasure to have this conversation, and thank you for podcasts. It's very interesting. I've heard the previous episodes. It's a very interesting resource. Our article is called "The Devil in the Details: What Everybody Should Know When Running DFT Calculations." Now, the reason why we decided to call it that way, we were doing a big survey of DFT literature, especially on the educational side, and we noticed that a lot of the past 30 years of research have been essentially neglected by the educational community, meaning that many educational resources that can be found, for example, in the Journal of Chemical Education, which is the top publication in the field, use very old and obsolete technique in DFT. Some of them are pretty good, but some other are not up to date with what the current research is. So we come from the research side. I'm a researcher in DFT development, and I've been doing this for more than 10 years. So we have quite a bit of experience on the research side, and we wanted to try to bring this experience to the computational side, to the educational side. So this endeavor started, was 3 years ago now, started to collect and analyze potentially interesting resources that could be used in an educational environment. For example, in an undergraduate class, like you were mentioning, my classes are both undergraduate and graduate. They're dual listed. So I have a rough mix of 50% undergraduate, 50% graduate.
Can I just stop? How big are the classes, the lab classes in computational chemistry?
Yes, we are a small university, so we don't have large size classes. So we range in between. I think the smallest class that I had was 5 people, and then the largest one, I think it was 11 or 12.
Oh, okay.
My first year. So yeah, they're usually smaller class. That obviously depends on the university. We have 5,000 students total, so we are a reasonably small research university. So the size of the classes is relatively small, but I think it's scalable to a bigger class, because the example that we chose are really not that big and complicated. That was exactly one of our goal when we designed this laboratory notebook. So yeah, let me say what did we do in the end. So we developed a laboratory notebook consisting of 16 experiences, actually 15 experiences plus one introductory course, or an introductory lecture, I should say. So these classes and these experiences have been designed basically to try to bring the research and the teaching environment closer together, especially the research in the past 20 years in DFT, in density functional theory, which I haven't said that yet, but is the most common method to calculate the electronic structure of molecules. So whenever you want to study a reaction on a computer, there's a very high chance that you're going to be using DFT, because it is the most useful or the most used method nowadays. Density functional theory is in principle exact. So we're using quantum mechanics. So it's a pretty tough topic, but we use approximation to make it simpler. So it can be used for molecules that are reasonably large now. I think the record nowadays is in the order of thousands of atoms. What we usually do in my research is something much smaller, something that goes up to maybe 10, 15, 20, maybe even 50 atoms, but we're still try to keep it small. We're chemists, we're not biochemists after all. But the experiments that we picked are much smaller. They are very common reaction that are taught in undergraduate classes, such as Diels-Alder reactions.
Do students use their own laptops, or do they use devices provided by the university?
Yes, you can use either. In my case, in my university, we usually use laptops, and that's why we chose these experiments so that they can be ran on laptops. There's other institutions that I know that have been using a similar approach, but they provide machines to students. Right now, we're testing this example on a online server that provides access to small calculations, and that eventually will be possible to run this experiment on the online server. We're working on that right now. So there are options. There are options. The easiest one, yes, of course, is to run the experiment on the laptops.
So do the experiments need software? Do they use Gaussian or do they use other proprietary software to?
Yes. So we try to make it more software agnostic as possible, or as software agnostic as possible. Of course, you have to run a software. The experiments are general enough that they can be running in any software that does quantum chemistry calculations. So it could be Gaussian, which is obviously the most famous one. It could be QChem, which is the one that we used to develop course because I am a QChem developer. It could be Spartan, which is very much used education environment. Actually, Spartan is using QChem in the back end, so they're tied together. It could be using really any other software, for example, open sources software such as Games or NWChem, which are very useful because students can download it and don't pay a license for it. So any software can work, really.
So we've worked with the WebMo people. Is
Yes.
WebMo possible too then?
I think I'm not familiar with WebMO much. I think they provide the interface, the graphical interface,
Right.
and they rely on some quantum chemistry engine, which I don't know what they use. But if they use any reasonable quantum chemistry engine, meaning if they can do DFT calculation, it is going to be possible to use that
Okay.
as well.
I just, the one thing I really like, the interesting piece where you say that modern research doesn't match what has been going into the laboratory.
Yeah.
Well, that's true of wet chemistry for years. And I loved in the paper where you talked about, doing these titrations. And I taught titrations in general chemistry for 20 years. I know that when I did research, rarely ever would I pull out a burette. So I think there's always been this disconnect between what's going on in a research lab and then what goes on with the students. And then that sort of eye-opening experience of, oh, this isn't really research. And I like last week we talked to Alex Spokojny at UCLA about his upper graduate inorganic class. And he said it was like bringing these undergraduates into his research lab. It's a neat thing to see that this is happening in physical chemistry too, that we're getting students to think about what it means to do experiments that are different, that are not what you would expect in a chemistry classroom. Am I correct?
Yes, you're absolutely 100% correct. In fact, we started actually the entire project from that analogy with the titration and the burette, because we thought that there's a really good analogy to computational chemistry side, where we teach the student something that look apparently very easy. I mean, you click some buttons on a computer and the results come out magically. In practice, this is way far from what's happening on the research side. And we wanted to, I think, give our student a better overview and a better view of what really happens in the research environment. And that is completely different than what is taught or what is available out there in the educational literature. Now, granted, I know many people that teach computational chemistry and they have very interesting courses, so I'm not throwing everybody under the bus, of course. The difference is that we thought that it would be very much important to make resources available to the community and researcher in the DFT, real DFT developer, to also enter the educational world and share our ideas, our resources to the educational community. So that's, I think, my goal with this paper and with this notebook is really to be one of the first to do that, but also to start a movement where research and the educational side come together and progress DFT and the computational chemistry community in general.
So so there's 14 different experiments weekly, so to follow a semester.
Yes.
And I sort of want to walk through the experience of a student in this class. And probably I want you, while I'm talking, I want you to think about one of your favorite experiment from 1 out of 14. And then I want you to tell us what that experiment is and what students have to do to solve the problem, because it is an open-ended
Yeah.
experiment. It's you have to solve this problem. How are you going to do that? There's open-endedness. It's not a cookbook. It's not push this button and get an answer. So I want to put me in the shoes of a student and tell me I'm on week 5 or 6. What experiment am I going to do? And how am I going to solve this? And what does my life look like for the next few hours in laboratory or week as I solve the
Yeah, so basically, tell you first how the notebook is divided. So as you said, there's essentially 14 real experiments that students can do. They're divided into two groups. The first group, the first 7 or so, yeah, the first 7 actually, really our goal with those experiments was to try to bring the student into the modern DFT world. So basically teach them that whatever they've been exposed to in the past, if they have been exposed to some computational DFT method in the past, was not necessarily the state of the art in the current research environment. And by doing that, actually, we do that by just presenting very, very small molecule, very, very small reaction, and ask the student to really perform the calculation with as many methods as they can, or as many methods as they want. So this happens in the first 3 experiments, and it happens also in the second 3 experiments. The division between the two is that we first focused on one of the most asked questions to ask computational chemists, which is which functional should I use? So these we try to answer in the first 3 experiences, where we present 3 different reactions, actually 3 different sets of reactions. And we want to show the student there are some reactions for which every functional is a good choice. Some reactions, so this happens the first experience where they can run any functional that they pick. They can pick whatever they want, run it, and pretty much the results are going to be okay. And the second experience, they'll start to see some problems. So these are what we named complex situation, where some functional are okay, some other are not. Most often than not, it's the modern functional that are okay and the older functional that are not okay. But we give the student enough freedom to experiment with the choice of the functionals, because again, they're small reactions, so they can run as many as they want in just a few hours. So, and then the third case is really very complicated case, extremely complex case, where no functional is capable of getting the correct answer.
Do they get frustrated?
No, I think they don't. Again, this class goes again, it's followed by a explanation class. Usually what I do is warn them before they start the experiment that they should not really looking for perfection, because this is, after all, a sort of a mimicking of the research environment. There is no perfection. I wouldn't say that they get frustrated. I would say that it's interesting to see that essentially, if they try 10 different functionals, they obtain 10 completely different answers. They might not know which one is the correct one, and in fact, there might not be a correct one. But that is exactly the purpose of the experience, right? Especially in the educational context, I think it's important to show student from the beginning that in a research environment is not always nice and everything's working correctly, but sometimes there might be problems. So really the first 3 experiences are designed to show all shades of possibilities in the choice of functional. And again, the most asked question is which function should I use, as I was mentioning before. The interesting part is we don't answer that question because there is no way of answering that question. So really what the
It
purpose of
reminds
this.
me of when I was in a research lab and I would ask the graduate students, I was an undergraduate, what solvents should I use? And like, well, you have to go find out what solvent or
Exactly.
combination of solvents you're going to need. I don't know. And so it seems very similar to my
Right.
experience as a lab chemist, a wet chemist.
Right, exactly. So the difference there is that instead of giving them everything ready and everything pre-selected so that the answer is correct, which is the usual approach, we let them free to explore. And purpose is basically to give the student sort of a freedom of choice, but also to grow them into what they will become as a researcher, meaning give them a little bit of critical thinking, give them hard choices that they would have to face, and show them how not everything is perfect in a research environment.
Have you had feedback? You've taught this 3 times,
Yeah.
correct? Yeah.
Yes.
Feedback from the students on that point, on that a little bit messier kind of no cookbook kind of laboratory class. Get feedback. Do they come out saying, I learned something, this was a great experience?
Yes, yes, that's exactly what happened. I have to say that mostly it's our graduate students that are very, very enthusiastic because they somehow use this in their own research. Undergraduate, they might not see it immediately because, of course, they're early stage. I didn't have any student that then decided to come to my lab to do a research project with me because, again, we're a small university, so the numbers are limited. But from our graduate student, we had very, very positive feedback.
You have students that are experimental chemists taking this DFT class so they understand when you're like one of the experiments is matching to experimental results from theoretical results. So do
Yeah.
you have a mix of experimental and theoretical graduate students?
No, we have mostly experimental graduate student again.
Oh, okay, that's good to know. Okay.
Yeah, we're our graduate school is reasonably small, and there's only one computational slash theoretical graduate student, which is my student, which worked with me on developing this project. So really, we had only exclusively experimental graduate student,
So are they now I'm going to get into the weeds a little bit. Are they inorganic or organic or what's their flavor? All
from all over. Yes,
okay.
we
Okay.
have 4 sections that are very active. My colleagues are very active in both inorganic, in all four inorganic, organic, pchem, and analytical chemistry. So I had students from all branches.
Our company has actually been interviewing computational chemists and
Mhm.
looking for a position. So maybe I'm putting a shout out there that we might be hiring. But one of the things I found, and this is one that it just came to mind while I was reading the paper, and from my experience, many of the computational chemists that I've talked to, the jobs that are becoming offered to computational chemists aren't necessarily in chemistry because they learn a process that can be applied in data science, and there's a huge need. As we all know, big data is big oil right now, is the new oil is data. So do you see that as students go through this
Yes.
process of learning, that they're getting ready for maybe a job outside of chemistry, and maybe some of that experience could you share with us?
Yes, yes, absolutely. I had several friends from my previous positions that, in the end, after getting a PhD in computational chemistry, ended up in companies that have nothing to do with computational chemistry, such as Google or Yahoo or Uber. Really, completely different field. I think you're absolutely right. The background that the computational chemistry gave you as a student, as a graduate student, is really wide, depending on whether you like more the chemistry side of computational chemistry or the computational side, or rather um, the computer side, I should say, of computational chemistry. You really have many opportunities. For example, if you obviously if you are more on the chemistry side, there's plenty of opportunities in the chemical industry that are open to computational chemists. But if you like more the computer side, the computer science side, there's really all the big data, as you were mentioning, field that's hiring a lot of student at
So
the moment.
when they come out, what kind of languages do they use in software? Are there specific things, or is it more of a thought process?
It's both, actually. Yes, it's really the thought process is extremely important. Once you know how to program, it doesn't really matter the language that you know, because you will pick any other language reasonably easy. It's not as hard as learning a new language, meaning speaking a new language. Computer languages are very interconvertible, I should say, probably.
It's more of the
You can
logic behind it, and more of
Right.
the systems of learning.
It's actually though both, because this was absolutely true up until maybe 10 years ago when I graduated. But right now, I would say that the computational chemistry community is really moving towards the more modern programming languages. So if you got a degree 10 years ago, you might be familiar with Fortran and not much more, maybe C++. But right now, this is no longer true. So even the computational chemistry community, which was stuck to the past basically for so many years, is now getting modern, and we use Python, for example, every day, all day, to analyze the data. We use modern data science software to again complement our research, such as R. We use yeah, we use
They can go into machine learning and
they
all the
can go, yes.
buzzwords. And that's actually really interesting. And a lot of students come in and think a chemist does this. And then when you come out and all of a sudden a chemist is hired by, as you said, Uber or
Mhm.
Yahoo, it's
Mhm.
a opportunities abound. And
I
so,
think it is. I think it is. Honestly, I think for a student that is not quite sure and he likes to do both sides, so is intrigued by the chemistry side and he's also intrigued by the computer side, I think this is the perfect field to be, because he can specialize and then decide later whether he wants to be a data scientist or a chemist.
wow. Well, this is great. And with that note, we all want our students to go off and be successful, and in from undergrads and graduate students. So I really like this sort of wrapping up this interview with this. Let's send our students off to do wonderful work and learn from us. So thanks so much for your time, and it was great
Sure.
talking to you.
Thank you, Julia.